There I am. Okay.
Hi, Richard.
Hi, sorry I didn't attend last month. I was getting a new computer and it kept crashing on me, so I was taking it back in and out and in and out and in and out.
Sure.
And I'm still trying to get it to work. So
Totally understandable.
if something goes wacky on me, blame the machine. You know,
We will.
the buck
Roger
starts
that.
here. The buck starts here.
Nice.
All right. Well, I think Laura's going to start today.
All right.
Hey,
So I just hot off the press as of today. So we've been working very hard with all of your data, or those maybe you didn't submit data, but many people did. And we've been just trying to make sure that we have every all the all the metadata on the data. So all the metadata correct. So we not everyone had put in the geographic data, geographic latitude and longitude in the format that we were looking to get it. So we had a student here at Sonoma State go through all of that data and then compare to where people said they were when they took their photographs and adjust things. Mostly it was just a matter of putting a minus sign because we were looking to have a minus sign. Some of you probably just assumed we meant east, but it looked like some of you were in China, and that didn't make sense. So we got that all sorted out, and so I have two new maps with some of that new data. So I just wanted to share with you. We're getting close to the anniversary of the eclipse, and then we'll do some PR soon. And I mean, it's coming up in a couple weeks. So we are trying to get some type of mega movie out for the, or a little video of all your eclipse photographs stitched together, but we had to get the data put together first, the metadata, because we need to make sure that where you were and your timing on your photographs was all correct. Um, so I'm going to share my screen and okay, can you see this?
hmm Yes.
All right. So the red lines are, of course, the path of totality. And I'm going to start with the participants who worked very hard, presumably, to get to the eclipse, and then something went wrong, whether it was clouds or you left the lens cap on or your camera mount broke. So these are all the folks who we I just want to recognize your hard work. Whoops. And your let me try to, why did that just do that? I don't know. Whoa. So there we go. Those are the folks who made it to the path of totality, or maybe they were at the path of totality, but were unfortunate to not get eclipse data. So some of you I know are in that bucket. And then here are all of the folks who were successful in getting photographs of the eclipse, and we have deemed your data as potentially good for science. So um, we're slowly making progress. And I can paste this. Maybe I can paste this in the chat. I'm going to try. We'll see. Okay, I'm going to stop sharing. That's all I have to share today. Short and sweet. All right.
Cool.
Any
Well,
questions?
next up, I think oh no, questions are a good idea. There's a question in the chat.
The GPS info is based on the reporter's information, which I'm sure we'll run across some issues there at some point, but we'll get there. Okay, any other questions from anyone? All right. Oh, who is off the coast? Yeah, I'm not sure. I think someone was on a boat though, if I recall correctly. I think someone posted in Discord about being that on that
Hmm.
boat. Um,
Oh, interesting.
but we can go and look.
I'm sure they were having a good time either way.
Indeed. All right. Okay. So I will put this in the chat and then I will introduce our speaker. Um, so I want to have a big thank you for Dr. Rafael Ati here. Um, you came in last year and joined our project, and you helped me understand some things about this very niche scientific field of eclipse research, research of the solar corona with eclipse data. When we were coming up with our gold standard and working to make sure that we got the data we needed and enough of the data. And so I just want to first thank you so much for your advice and also for coming in and helping us make the Discord positive again. Sorry about some of those situations. So glad that you stuck with us, and I'm so excited to hear what you have to say. Raphael is a research physicist. He was at Goddard Space Flight Center when we first started working together. I think you're still affiliated with
I still am there, please.
Goddard.
I haven't been fired yet by the new administration.
Wonderful. Great. So glad. You never know what might happen tomorrow. So I'm glad you're still there. And I know the last I remember you said you had that you do study jets and plumes and such, in fact. So
Yeah.
um, in any case, so we're very excited to hear what you have to say today. And also, you've been taking just stunning photographs of total solar eclipses and doing amazing processing with your data. So, with that, please correct anything I've said or add. Wait,
Yeah, it's just you're just a minor correction. It's
yeah.
not nothing wrong. It's just that you told me about jets. That is true. However, I didn't have time to put anything about jets in my presentation.
Oh, that's totally fine.
And
Don't you
but I
worry
can
about that.
talk about it. I just don't have a slide for it.
That's
Um,
okay.
I will focus on the actual Eclipse experiment, the imagery, and all that.
That's
Uh,
what we want. Perfect.
um, and yeah, so first of all, I would like really to thank you from the bottom of my heart for having me take part into this absolutely fantastic project that you've been leading. I really had a blast working with all of you. And I sincerely hope that, okay, we're not going to have an eclipse anytime soon in the continental US. But, I hope that we can work again together on future eclipses elsewhere in the world. I'd be really happy to do that with you guys. So yeah, if anyone, in your team wants to is planning something for the next eclipse, please let me know. And if I can do anything to help, because I already know you guys, so that's of course always better to be with people we know than with complete strangers.
Let's do it.
Um, all right, so without further ado, all right, let's talk about my talk. And I'm gonna try to share that, but because I have a huge screen, I never know how it's gonna appear on yours. So let's try that. Let's see if you have something, if you're saying something. All right, that's whoop, feel like the starship that always fails to launch. Sorry, that's a misfire there. Uh, I think that's the one. All right, share. Yeah, that should be all right. You see the my presentation? Hello, can you hear me?
Yeah.
Yes, it looks good.
Okay.
I see only PowerPoint.
You see only PowerPoint. That's good. Okay, now let's try to play that and tell me if it's pixelic or not from your end. Is that okay?
It is a
Looks good.
bit cut. Oh, there it goes. Wait, there it is. But I see notes and everything.
Ah,
So I
okay.
think we
That
see
we need
the
to swap that. Yeah,
presenter.
that's always, I never know what you guys see. Swap displays. All right,
There
there
it
we
is.
go.
Perfection.
It's good? Okay. Um, can you see the very noisy background on the right? Yeah, it appears.
Mhm.
We see the colors and the pixels.
And
Yes.
it's very pixelic. Okay, that's good.
Yes,
That
yes.
I can illustrate on some points there. Okay, good. So hello everyone. So I'm Raphaël Atier. I'm a solar physicist and solar astronomer at NASA Goddard Space Flight Center as a contractor with George Mason University. And I hope I'll be there as long as possible. And I will talk about my Eclipse experiment that I did, in April last year, as also that I did sort of alongside, and all the preparation was done alongside the Megamovie project, but I did have sort of an independent experiment. And I even rolled out the possibility of formatting all the data so that it can also be used by the Megamovie project. But I've been very delayed at processing everything, and I will show you here an sort of work in progress, and I'm supposed to publish all of that by the mid of next month, around mid-April, hopefully. So let's go. We will talk about the preparation of that eclipse. And then we will go into the imagery of the total eclipse. I will briefly mention the science, and actually, I will not talk about future eclipses because I removed those slides. Only if we have time, though. All right, so let's talk about eclipse preparation, and I'm sure you will find a lot of echo in your own preparation. I am sure many of you have been through lots of emotional roller coaster with that eclipse, I am sure. And my experience was not different. So initially, NASA had planned a viewing site for me at the in Dallas at the Dallas Arboretum in the botanical garden. It was an absolutely magnificent place where I was supposed to go, with security and with people to help me set things up, and so everything was happy in the best world. And this is what I had planned to do. I was supposed to have a refractor, an 80 millimeter refractor, to have this field of view that you see here. Whoops, let's go back. This field of view that you see, which have about an 11.2 solar radii of width. And it was supposed to be imaged with Nikon Z7 Mark II, and it was supposed to be coupled by another lens of 180 millimeter with a polarized camera. I will explain later what is a polarized camera, and that would give me a very similar field of view that you see here in orange. And another instrument, which would have been a Takahashi 60 millimeter diameter with a 256 millimeter focal length, coupled with a modified camera that was more sensitive to infrared, and that was supposed to give me this field of view in the dashed line. Okay, so few days before the eclipse at NASA, we got a regular briefing about the weather. So each day we sort of had updates and until the day leading to the eclipse. And so this is an example of those maps that we were shown during these Teams meeting that we had. That was on, let's see when that was. I can't really see where that was. I think that was April 5th. All right, we're 3 days before the eclipse. And we could see that in the region of Texas, when Texas had been, it's a bit like forecasting the result of a championship or a Super Bowl. Everybody was saying that Texas is the best place to be to see the eclipse. You probably all remember that, I hope. And they were giving this sort of climate prediction that, given the statistics of past years, places that would be really the worst would be, for example, Maine. Maine is really the place not to go. And so I'm looking at the prediction, and we see all these clouds. And so are starting doubting a little bit what's going to happen. And so I start to look at other maps, and Goddard also are using the same. And no matter what model I look at, I am seeing that in around Dallas we have a high probability of cloud cover. And then I was looking also at that, and that's also very important. And that was not really something that people were talking about, but these maps, they actually show the amount of aerosols that you have in the air. And as we'll explain later, my experiment is about polarization, taking polarized imagery of the corona. And the thing is, when you have lots of aerosols like carbon monoxide, dust, nitrate, sulfate, these are aerosols that create a bias in the polarization signal. So basically, the light that comes through these kind of aerosols gets biased, and it impairs the data. So I had a combination of cloud cover forecasted and lots of a lot of those aerosols that were predicted to come over the sky over Texas. So you can see here the evolution of those forecasts, and that is correlated with the level of stress that I had when I was looking at the forecast. So you can see April 6th at midnight Zulu, 6 Zulu, 12 Zulu. And so at that point, right on the, completely on the right, I think I was going to lose it completely because I had my flights, of course, booked for Texas, Dallas, and I didn't really have a plan B, right? So I decided last minute to look at what were the new places that were forecasted to be the best. Well, those places happened to be Maine. Maine, the very place that was supposed to be the worst in terms of prediction for climatology. When you look at the statistics of past year at that time of the year, that was the place not to go. Well, this is where I end up going. I took a flight to go to Manchester, New Hampshire, because there were absolutely zero hotel available in Maine. They were all fully booked. So I took the hotels available that were the closest to the path of totality, understanding that I will have to drive, of course, on Eclipse Day. What could go wrong? So, so I did. Woke up very, very early. And in the meantime, I was actually talking to my co-author here, Nicolay, who is a professional weather forecaster at NASA Goddard, who is giving me every single hour the nowcast of where was the cloud going to tell me where in Maine I should go. So that was a serious teamwork there. When I arrive on site in near Mount Katahdin in Maine, after an about 6 hour drive instead of the 4 hours something predicted by Google Maps, I start setting up my equipment. Believe it or not, we are 15 minutes before totality when I start setting up my equipment. 15 minutes before totality. Right at that moment, there is a nice lady who comes and see me with batteries that I'm plugging into the computers. And she's rushing to me and ask if she can plug in her laptop to one of my batteries because her laptop is out of battery and she needed to send an email. So imagine you remember the gauge of stress? So that was actually completely past the red, of course, and the gauge was completely destroyed at that point. And I have a very nice lady who is asking me to plug in her laptop in my battery because she needs to send an email to her boss. I mean, who does that 10 minutes before totality? So the thing is, I had NASA stickers, I had NASA written all over, and so I didn't want to be rude, and also I'm a bit of a soft touch. So of course I accepted that she uses my battery, and so I sacrificed a few precious minutes so that she can send that email. In the meantime, I was trying to do other things. And then after that, of course, she notices that I speak that I had a French accent, and she's starting to engage a conversation, telling me that she's also French speaking. And no, of course, I wanted to be nice, and I didn't tell her to just, stop talking because I need to set things up. Anyway, long story short, she was finally unplugging her computer 3 minutes before totality. And we're 3 minutes before totality. I still haven't pointed my telescopes to the sun. And so I start doing that. And while I was launching the software to acquire the images, totality started. I still haven't started my software. So you can imagine that I had these experiments being set up for which I prepared for months. And we're in totality, and I haven't started even the software. So I lose 1 minute of totality. The software are on. I don't even have time to take care of proper focusing. And so I crank it only once, hoping for the best. And I took the images. And I didn't even look at what I was taking. I had no idea of, whether or not I was focused right. I just did it by muscle memory. So because of all of that, I had to sacrifice two of my experiments, which were the artistic one, to preserve the scientific experiments. And so I ended up having my 80 millimeter coupled with an astronomy camera that I had also there, and to run the small 180 millimeter focal length lens with a polarization camera, which was the most important of that experiment. So this is basically what I had time to set up during the very tiny little amount of time that I had. And the only way I was able to actually do that is because I had rehearsed that at home, sacrificing two other two other sort of artistic experiments. So we have this 80 millimeter refractor, that's the red one, and coupled with the smaller one, which is actually the most important experiment of this entire thing, which is the where you have the polarization camera. So let me talk a bit more about what is a polarization camera. So polarization camera, that's what you see on the left. It is a camera where instead of having the RGB filters that you have on top of your CMOS sensor, they replace those little photosites by linear polarizers where each of them is oriented in a different angle. And so instead of having RGB, which are 4 color filters, which we call also the Bayer matrix or Bayer pattern, we have 4 of these linear polarizers. So that contrary to how we were doing that in sort of physics before in past eclipses, where people would have sort of a filter wheel and would rotate after each shot to have a different shot at a different with a different linear polarizer, then basically you can take here 4 shots in one at different angles of polarization. So this is how you can visualize a polarized eclipse. So an eclipse that you shoot with a polarization camera. Here, the color are these set up in what we call the HSV color space, where H is the angle of polarization, S is a degree of polarization, and V is the amount of polarized brightness that you have. Why do we want to get polarized imagery? So the polarization of the corona comes from a physical effect that we call Thomson scattering. And when you take that polarization signal, you can do some inversion to infer the actual velocity flow of those electrons. And so here is an example of those flow maps that we want to have. And these very flow maps are not done with the eclipse imagery. I wish. I've done that using a different kind of analysis with space instrumentation, but it just to show you the kind of thing we would like to do ideally with eclipses. So let's go into the actual imagery that I took during the eclipse when, I'm like you right now. So that means that I took the imagery, but I didn't know what they were looking like. And so here you're discovering, like with me, when I was back to my hotel and I was actually starting to look at the images. So this one is the longest exposure that I had, which is actually the number you see at the top is wrong. I forgot to correct that. That longest exposure is just about 130 milliseconds. So that's 0.13 milliseconds. It's from the polarization camera that is extremely sensitive, very, very low noise. And so with a DSLR, you will need to, for having the equivalent, you will need to have an exposure of about 2 seconds or 3 seconds at least. You can see that the field of view is actually greater than 10 solar radii on one side. And you can see that I didn't have the time to center the sun, which is okay because I actually wanted ideally to have more than 10 solar radii. And so that's okay. I can have a corner and analyze things down to the, for example, lower left corner, and I would have more than 10 solar radii. So here is the an image at 1.3 millisecond exposure, and this is sort of a raw image where we converted the the imagery to this HSV color space. And so basically when the color varies, that means that the polarization signal is different. So that means that the electron, the flow of electron is different. And it also different when the brightness changes as well. So all of these variation tells us things about the structure of the corona itself and the velocity of the electrons that are escaping from it. So it is telling us something about the solar wind. From there, you can even guess, because I haven't rotated the field, so I don't really know where the poles of the sun are in that image. I didn't have time to take at what angle I was angled. So, but we can already guess where the poles are. This is likely to be about on that direction where we have less structure in this polarization image. So here I've increased the exposure time by a factor of 10. I have other intermediate exposure, but it's just to show you simply a summary of the scanning of these through this exposure. So this is 1.3 milliseconds. This is 13 milliseconds. And this is again 10 times more where you start seeing a lot of the illumination of the sky itself, which seems to be rather unpolarized as you are really away from the corona. So here is what we called composite. This is an intermediate result that I generated, and in around the center, it's already itself a composite between two different exposure times, so 1.3 and 13 milliseconds. And you can see the difference of what we can get with when you have an exposure time that is 10 times more, the 130 milliseconds. You can go a lot more, a lot farther to see the corona. And so a lot of other experiments, they usually focus on that inner part where you have the 1.3 and 13 milliseconds exposure. That's typically where how wide, how far you will see eclipse imagery in general for scientific experiment. I was interested in looking even farther out, and luckily that succeeded, and I'm very happy about that, especially given all the stress that I had and the uncertainty, and no idea whether or not I had a good focus, and I did. I have enough structure all around there. That's all I needed. All right, and so here's an example where I'm going to switch between the composite with the 1.3 and 13 milliseconds combined and the 130 milliseconds. And there's a lot, so much more than I could capture. Look at the bottom, the blue there. Look at these rays. They look like jets, or maybe they're pseudo-streamer rays where you have currents, lots of electrons going there. So these are very interesting places to look at. And so it's interesting because we can combine that, of course, with the imagery from other instruments in space who are looking at that on different wavelengths. So another thing I want to talk about is, just so that you could actually learn something from your own imagery. So you've taken images probably yourself with your camera, and you may not have you may have missing exposures, for example. You're out of stress, you may forgot something, maybe you didn't plan the exposure correctly, and maybe you end up with underexposed shots because you had, I don't know, a clouded sky a little bit, but still enough to get something. So what can you do if you have underexposed shots? The thing is, you can do a lot. And I will show you. Imagine that you have this situation where, if I hadn't taken the 130 milliseconds, I would basically I would end up with that, for example. Now let's take an example with a regular camera because polarization camera you will not be able to compare. So here I'm taking imagery from the previous eclipse in 2017 that was taken with a regular DSLR, much closer to what a lot of people from the Megamovie experiment had. So here I'm shooting at 800 ISO. At 1/250 seconds exposure. It was with the Takahashi 60 millimeter diameter. I forgot exactly its focal length, but basically the ratio was at around 6 or 7. And so this is a regular DSLR. The bit depth of the sensor is 14 bits. Nothing extravagant. You can get an intensity value anywhere from 0 to up to 16K where it's going to saturate. And imagine that you only have that. What can you do to still exploit that images to see farther out in the corona? The thing is you can, and some people believe they cannot, and that's all they get. Now, if you take I'm talking for those who are not too much experienced with Lightroom or Photoshop, just showing you simple things you can do to bring out really the depth of the data from your imagery. So imagine you're in Lightroom and you simply change the exposure by 2 stops, which is equivalent to multiplying your sort of brightness by 4, or basically emulating a longer exposure that is 4 times longer. This is what you would get. So I'm going to circle back. You're here, and now you're here with the same photograph. Let's continue that game. We'll go to +4 stops. You can reveal still a lot more, and it is still the same photo. And you're not saturated. You're still not saturated there. Here, 5 stops times 32 longer equivalent in exposure times. Times 32. So that means you went more than 1 order of magnitude. And so sometimes, people would prefer to have all of those. They would actually take as many images in different exposure times so that they would see the same thing with maybe less noise, but with a longer exposure time. But here you can still do that with a single photograph. And that's with a very, very old camera, actually. It was a Canon 450D. It's a dinosaur in terms of camera. So you can imagine that with anything that is even 10 years old, you get things that are better than that. And so this ability to, go deeper into your photograph to boost really all those faint signal, the ability to do that is quantified under what we call the dynamic range. And you'd be surprised at the incredible amount of dynamic range that modern DSLRs have. So if you have such images, please play with Lightroom or Photoshop to increase that brightness and have a look at what it looks like. And finally, the point I want to make there is that when you do that, at some point, you're going to run into the issue that you're going to start seeing these little pixely colored pixels. And this is what we call noise. There's this sort of high frequency pattern. That's what we call noise. And this is what we're fighting against. And so that's why, with the Megamovie project, they came up with a gold standards of exposure to take many different exposures to make sure that you're going to bring the light of the faint corona at sort of the right amount of signal without causing too much noise. And you have to do that because maybe you have dozens a volunteer who are taking photo, you don't know what camera they use. So you need to account for people having also old cameras. But it is true that someone who's having a very recent mirrorless Nikon Z or Canon R, they may not need to do as much of these exposures. This is why I wanted to really show you that if you're in that case, that you haven't taken a lot of exposure, that's actually okay. So if you really are not familiar with how I did that with Lightroom, so I took a screenshot, and where I place the exposure, it's when you go under light, and you see on the top right, where's my mouse there? This is what I play with, and I prefer doing it with Lightroom versus Photoshop because Lightroom is actually using a unit of stop, which emulates exactly what the your camera would do. The +1, +2, +3. These are units of stops. So what are the lessons learned there? Um, so when you're planning an experiment that is really scaled to the team that you're supposed to be with, that you're supposed to have with you, yeah, this is great. But when you have to pivot at last minute, that is really not good for just one person. So you need to be prepared to make sacrifices and you need to be prepared to make a plan B. If I had known ahead of time that I will be in that situation, of course, I would have planned things differently. But luckily, even the entirety of these experiments that I had with me in the car, so given more time, I would have maybe been able to do all of that. Um, well, the thing is, I had to make a last minute sacrifice and I got really lucky as well. So basically, don't do what I did. So what worked is the fact that all of that was sort of still a mobile setup. I could have everything as in a carry-on, in fact, so that I don't have to worry about luggage being lost. So that's an amount of stress that uh, um, you don't have to deal with that. And I know other people at NASA Goddard who planned for an experiment at 100 times more the cost of mine, who couldn't take a single image because they had a very non-mobile equipment, a huge telescope that was shipped beforehand to Texas, and it was there. It could not be moved anymore to another location, and so you're basically there at odds of the weather. Um, all right. So just wanted to conclude on these the eclipse science. And I happen to be a part of the Punch team. The Punch mission is a new mission and has been launched a few days ago. Yay! And if you haven't seen the launch, you can look at NASA Punch and you will see the replay of the launch just a few days ago. So I'm part of the team that actually I lead what we call the working group 1A for the flow tracking of the solar wind. So my team handles the delivery of the flow maps, the solar wind flow maps all around the sun that Punch will be able to capture thanks to this polarization imagery that he's going to take. So it's going to create an artificial eclipse, only visible by its camera on board. And the mission is made of 4 spacecrafts. You have this NFI at the middle, which is creating this artificial eclipse up till about 15 solar radii. And then you have the Wi-Fi spacecraft, 3 other spacecrafts. It's a constellation, and they are combining their imagery to produce what you see on the right, a sort of this giant eclipse where you can see up till about 90 solar radii. So it's about 45 degrees from the side of the sun. When you go away from the sun at about 45 degrees. So the field of view is 90 degrees. So it's huge. It is huge, and we'll be able to deliver maps of that solar wind for the first time ever in a permanent, systematic way. So every 6-hour cadence at least, we're going to have an updated map of the solar wind thanks to the polarization camera that we have there. So thank you very much, and I don't know if you have questions. Go ahead.
Very nicely done. Thank you very much. Uh, I I once heard it said, I can't remember who said it, that luck happens when preparation meets opportunity.
I love that line. It's really
Yeah,
good. Yeah, you're absolutely right.
and you did the preparation.
That is right.
Very nicely done. Thank you.
Thank you.
When does Punch start taking data?
So it's in commissioning phase now. So it launched like last week. It takes 90 days for the commissioning. So that means it's 90 days. It's because the four spacecrafts, they are slowly separating all around Earth. So they're in a polar sun synchronous orbit, that's going to look constantly at the sun. And so they are going to be evenly distributed around the Earth, like, carousel. It's really like a carousel because I like this image because as they rotate around the Earth to maintain always the same exposure, they also are rotating on their own axis, you know.
Mm-hmm.
And so it reminds me of the cups at Disneyland that as the
Mm-hmm.
whole thing turns, all of the cups are turning. And so 3 months we're gonna have I think first public release probably a little bit after this J plus 90 days of commissioning phase. We will have probably I have to have intermediary data anyway to fine tune the algorithms that's gonna process the solar wind maps. I will try to see with the PI if I can share some of that on public intermediary.
Eventually, I'm sure you will be able to. And then how does the like what we're seeing in your polarization maps, how does that kind of map to the like one you said Punch still isn't going to see all the way into the photosphere. Is that what you
Uh, no, right. Punch, because it's a coronagraph, it's occulting the sun itself, so
yeah.
you cannot see it in the photosphere. And the connection with, say, my eclipse imagery, for example, in for the next eclipse, because this one really is the first time that I was doing a proper, I mean, proper, was designed to be a proper scientific experiment. It ended up to be very improper, but um, the thing is, it doesn't have the huge field of view of Punch, but what matters is that it is in, let's say, Punch field of view contains that field of view, that smaller field of view, but that smaller field of view has higher resolution.
Mm-hmm. Yeah.
So I'm interested in that overlap so that I can see if with Punch, fingers crossed, if we have a successful eclipse on 2026, then we will have Punch then. I will look at the overlay, wherever the overlap, and see if what we see in Punch, is it resolved or not. Basically, if if something is resolved, if you look at even higher resolution and you see something with even more details. If not, that means that, right, the feature we see in Punch are actually resolved.
Mm-hmm.
Because, far out, eventually, there are what we call mesoscale structure, that are defined by a certain shape, and nothing much happened to them as they propagate all the way to the Earth, apart from the natural expansion due to the expansion of the magnetic field itself as well. And it just, propagate like a cone, and so, yeah, there could be structure within that mesoscale. I mean, we don't know. Some people think no, that there are no substructures, but this is why, what makes me curious. We will have Punch, and during a real eclipse, we will see if what we see in Punch is more detailed than what we saw.
Very cool.
A question from me. Uh, with the Punch, will you be able to have it aligned so it actually captures the sun in eclipse rather than having its artificial eclipse
Ah,
at the
um,
time of the eclipse? Or,
I don't think, no, I don't think so.
okay,
I
so
don't think so.
it's just a complementary set of data then.
Right, yeah. The eclipse, yeah, I think I understand what you meant. So basically, if we have in 2026, if we have that
Hmm.
real eclipse, that's going to be in a very narrow part, crossing a bit of Iceland and Spain. if that shadow is gonna is if basically punch is gonna go through that shadow. Um, is that what you meant?
Basically, yes.
Okay, so that will not happen
Okay.
because, as I mentioned,
Yeah.
uh, Punch is a constellation of 4 satellites that are all around Earth, and you're gonna
Hmm.
have maybe the shadow cast by the moon cannot be over the 4 satellites at the same time. So at
True. Yeah.
best, we can have one that being occulted, but the other is not. So we cannot have that combined imagery all
Hmm.
at once. That's for sure. That's not possible.
Okay.
So is it like a Ferris wheel from dawn to dusk?
Sorry, can you say that again?
Is it like a Ferris wheel from dawn to dusk and north and south? Like it's going on the terminators and over the poles, those four.
Yeah. I mean,
I mean, they're
it's like
stationed.
it's very similar to the orbit of SDO because SDO is in a polar and synchronous orbit as well, I think. So you have the Earth.
Mhm.
Um, I have a sun over there. So you have the Earth, and you basically have
Yeah.
uh
Mhm.
like this way. Then I think there may have times there may be eclipse seasons when the Earth is occulting the satellite, but then that would be a huge occulter, so you wouldn't see anything at all. Um,
Hmm.
I don't know if I answered your question, Nora.
Yeah, I guess I also don't know how close. I haven't been paying attention to Punch recently in terms of its orbit. It's not out at the L1 or
No,
it's
no, it's much.
around
No, no,
Earth,
no. It's
right?
in Leo. It's a low Earth orbit. So
Yeah, yeah. Yeah,
yeah,
so it's a polar orbit, dawn to dusk polar orbit, basically.
yeah.
Yeah.
I didn't know that term, but I guess so. It's about
Mhm.
690 kilometers, something like that.
Yeah.
Okay, its orbit is over the terminator then,
hmm Yeah.
or at least depending on how the Earth rotates in its orbit, that might shift.
I'm sending you the a link where you
Yeah,
have.
because all those kind of orbits they precess, and so
Yeah.
they will be dawn to dusk, and then they'll go back to. So that's what Raphael, as you're saying about the Earth's going to get in the way as it precesses and it becomes a,
Yep.
midnight noon orbit, and then it'll go back to a
Hmm.
um. But that it takes it just depends on how it was launched.
Yeah, I was hoping to have a more exact thing, but yeah, down. Oh, actually, they use your term, so down to dusk alignment. So yeah, it's like SDO also has eclipse seasons.
Hmm.
So it's gonna be, yeah, probably the same, except that you have 4 satellites all around the Earth. So I don't know how these. It's not gonna be simultaneous, probably not simultaneous eclipse.
No, probably
It could be
not.
interesting.
No, and it only takes about 90 minutes to orbit at Leo.
Yep.
So it's just constantly moving around. So yeah, it's kind of like, yeah, it's cool that they have four of them. And then they're all pointing at the sun, of course. So they're kind of doing this.
Yeah. I like this movie that Craig's team made. Craig DeForest is the PI of the instrument. Where is that? Let's see.
Yeah, we're in my territory with the dawn to dusk because I'm
Cool.
I study the aurora, so that's what we talk about. Very cool. Other questions people have? Thanks also for sharing the. Yeah, I liked what you showed in Lightroom. I've been thinking because you said something a year ago about this, and so I've been thinking about it since you said it, and basically I had gotten to that point. So, but it was helpful to see it, yeah, in that graphical form.
If that can be, if that inspires you for the Megamovie processing,
Yep.
um, yeah, let me know. You may have. I don't know how you do the selection, but if you realize that you need more samples, I mean, if you don't have enough samples because
Right.
maybe you ruled out some data series that were not complete in terms of, having all the exposure, maybe you ruled out those who don't have all the exposure, or, thinking that you don't have enough. you could relax maybe that constraint,
Yeah.
and with this kind of consideration that okay, you can actually do as good with less. That's
Well,
possible.
and luckily you did say those things in Discord, and people did upload with when they had the very nice cameras, they did upload fewer images, but
Ah, I
more
see. Okay.
pixel exposure. So we did get that. Uh,
Okay.
yeah, so I think, and there were some Z
Yep.
cameras, and so
Yeah.
yeah,
With
it's been fun to start looking through what people sent and the images, and it's a lot of processing. We're trying to figure out the best way to start, actually.
Okay.
A lot of
Um,
data. We have 1.19 terabytes of data,
that's okay.
including the
yeah,
calibration frames. So
yeah,
good job, y'all.
yeah,
You should
The
feel very proud of yourselves. I'm very grateful
yeah,
to everyone who submitted data. Oh my
yeah,
gosh.
yeah. One other point. Thank you for pointing out the difference in the way different editing programs handle their light, eh, their brightness adjustments. Very interesting that the user's manual never says that.
you're right. I
In,
actually was like you, was a bit frustrated with that.
hmm yeah,
At first I was doing Photoshop because that's what I used to combine
hmm
qualitative combination. Normally this combination that I show normally I program that in Python code, but I usually start with Photoshop just to have an idea. And I wanted to do that test with the brightness, and I was frustrated because I didn't understand the unit they were using, and
yeah,
the photographer I couldn't really relate that with my camera.
yeah,
And then I looked into Lightroom and say, oh, that one is a bit more natural.
hmm
And but I'm interested to see with other if other software are even more intuitive or not. I haven't tried the any Apple software yet.
Yeah, that's cool. All right. Any questions? Any more questions for Dr. Ati? So there's a bunch of stuff. There were a bunch of chats
Oh yeah, I'm seeing that now.
when you were talking. I didn't know I always wanted a polarization camera before now.
Okay, they are expensive, I must tell you. They were bought with a research grant
Research
fund.
money.
Yeah, that one in particular. Last year, I bought it last year. It was about $4,000. I don't know, maybe it's a bit less expensive now, but it's still, wow.
Yeah. Although I have found that a lot of our volunteers, they save up for explicitly this type of work. So it's a big hobby for a lot of you.
yeah.
There is a question from Hannah. Any suggestions on looking to get into using a polarization camera? Wait, yeah, I guess I answered that. You can have, I mean, actually, you could use another polarization camera from a similar brand or the same brand with a smaller field of view because what I did there was very specific. I wanted to have a huge field of view, but if you want to have just the inner part that I showed, let me go back to that slide. There, the inner part. You could actually found the polarization camera is not more expensive than a recent DSLR. You can find it for a couple of thousand of dollars, so that's much more affordable. And it's tiny. It can hold in my hand. Where do I have it? Oh, I have it here. See how small that is.
Oh,
It's in the
it's
palm of my hand,
adorable.
and that is with it's even smaller. What I have here is simply the adapter rings to go into the telescope. It is tiny, and so it's industrial grade, so very low noise. You don't need cooling, so it's very easy to power. And yeah, if you don't need the big field of view, you could get high resolution Eclipse in polarization. Um, I would recommend then for the brand. I would not recommend the brand that I had because the acquisition software is clunky as hell. And with another brand like QH, I would recommend, I think QHY, I think they do it. They have much better software.
Nice. It looks like he has a question.
Yes, I do. Is my microphone working?
Yeah, yeah.
Yeah.
Okay, great. Always forget to unmute. So you're going to get some polarization effect from scattering in the atmosphere. And the question is that would likely introduce some bias. Uh, do you care about that, or can you like take that out because you know the angle at which you were pointing up at the sky?
I couldn't hope for a better question, actually.
Well, you know me. I'm
We'll
an
send you
engineer,
your
Raphael.
$50 later, Heat. No. Just kidding. We did not pay Heat.
All right, then let me pull my where did I put the other PowerPoints? I have a slide exactly for that to answer that question. Let me just check. There.
And then you have to hit share again.
Yeah. I'm still looking for the thing. I think that's this one. Yep. And yeah. Let me share again. All right. There. Okay, so let's talk about cross-domain science. I mentioned in an early slide that I was caring for the scattering of the sun itself, and not just scattering, but the actual depolarization that can be created by the sky itself when it is filled with aerosols. DKIST people, which is a huge solar telescope installed in Hawaii, could already establish that even at their altitude, the sky and the aerosols in the sky, they are a killer for, in terms of bias. They highly bias the measurements of the magnetic field of the sun because there are spectropolarimeters, so there's polarimetry involved. So I care a lot about that for eclipses. And so for the next eclipse, I have the craziest of projects. And I am still interested in collaborating with people who are more expert than I am in aerosols, because I don't know squat about aerosols. I just know what they cause, but really I don't know how to access proper observations of maps of aerosols. I am very ignorant. What I'm an expert at is building drones, because that was one of my former jobs. I can build custom drones. And so I can basically surround myself by drone experts and tell them what exactly I need. And the idea would be to take in situ measurements of the column of atmosphere that's being shadowed by the moon, and have multiple constellation of drones taking these in situ measurement, and we combine that with satellite imagery of these aerosols to try to have really the most accurate map of these aerosols along the line of sight, as long as possible. Of course, the drones are not going to go to the stratosphere, obviously, but combining that with satellite imagery, um, I would like to have an eclipse experiment that will actually have a map of the depolarization of the aerosol, so that I could compensate and remove that bias from the polarized imageries that I'll take. Hey, are you working in that field, aerosols and?
I'm not. I don't work in aerosols. We do have at our facility an aerosol tunnel, which is I'm going to say probably on the order of magnitude of um, 100 meters long. Uh, I do know some people doing uh, optical comb based spectroscopy, And so I'm going to ask him next week, I think, when I see him. Hey, Daniel, do your dual comb interferometers, can you get the polarization information? Because now he's looking through a really long column of air when his application is remote sensing of um, pollutants. We cannot say greenhouse gases anymore, but we can say uh, you know uh, uh, pollution, air pollution release.
That's very interesting. I'd love to, if they're interested, I'd love to connect with them to ask questions.
I'll ask him. He's a postdoc. We stole him from NIST in Boulder, and so he's currently postdocing here with us, and he's um, uh, he says he wants to bring up our capability to make optical, dual frequency combs. And so I've challenged him with, can you get it to where a high school student or middle school student can build a frequency comb? And about a dozen years ago, I did something where I put something together using surplus optics, so you can build a Michelson interferometer using a laser diode, like a laser pointer. And so obviously a frequency comb is a lot more complex than that. And so Daniel is kind of, all right, I'll think about it, but as a outreach kind of STEM education kind of thing, that it's an interesting idea. Can you help someone?
Please follow up on that, and I'll try to remember also to follow up with you if
Yes. Yeah, absolutely.
Okay, well, I think we're at the end of our time. Hannah, did you have anything else on our agenda?
No, I think that's everything for today. And what a meeting it was. That was a really great presentation. Thank you, Raphael.
Thank you very much.
Thank
Dr.
you,
Ati.
Raphael.
Thank you, Richard. Thank you, everyone.
Thank you for your great
Yeah,
question.
it
He.
was great to see you, and great to see everybody, and and I didn't get it snowed on us the night of the lunar
Yeah.
eclipse.
Oh, no. Yeah.
Yeah.
Yeah, it rained here.
Yeah,
Yeah.
Calgary was overcast with snow as well. So,
But if you look on Discord, there's some beautiful photos.
yep.
Yeah, George, your photos were very well received on Discord. I shared on behalf
Oh,
of
you're
George.
muted. George is muted.
Okay.
George, you muted.
Oh, and Hero had a good shot. That's great.
Mm.
You, let's see if I can transfer me over here.
We heard you. We heard you.
Oh yeah, you're coming through.
Yeah, let me see if I can share my picture.
Wow.
Wow.
That's the full moon. That's not the one I want to show.
But still,
Yep.
Very nice.
very cool.
Hold on. Let's see.
Stunning.
Nice.
There you go.
I have a question for people. Have any of the lunar satellites looked at the location that the historical records from, I think it was the 1100s or 1300s, an English monk saw a flash on the edge of the lunar disk, and in retrospect, I think it was a meteor impact. And I was just wondering if anyone had taken a look to see for a new crater on that side of the moon, or have all the orbits just been basically equatorial? Or has anyone?
If you looked at LRO, lunar reconnaissance orbiter.
Okay.
They mapped, I think, almost the entire surface,
Okay.
and to very high resolution and in multiple wavelengths. And so you should
Okay.
look at their data.
Okay. I can't recall off the top of my head the uh, actual location, but looking at it, it was, if I recall correctly, it was at about the 2 o'clock position that the monk wrote down that he saw this flash on the moon, but it wasn't reported because at the time the moon was supposed to be perfect, like everything else in the sky at the time. And so he didn't want to be burned at the stake for having seen something that wasn't allowed.
Yeah, that sounds familiar.
Yeah.
Yeah,
Sounds,
so you should look at the website. They have the data available, I think.
thank you for that reference. Thanks.
And then you
Yeah.
can report back to us what you find.
I shall do. It may take a while. I shall
Okay,
take
I
one.
think Hiro wants to share, and then we will end after this.
Okay.
I do love the sharing.
どうぞ
Yeah.
よろしくお願いします。
Wow.
Kire.
ありがとうございます。
はい、
That is
ありが
super
とう
cool.
Hiro-san. Takahashi-san, excuse me.
Yeah.
All right.
Beautiful.
すごい。ありがとう. Thank you, everyone.
Okay,
It
and
has been a
thank you all.
pleasure.
Thanks.
We'll see you next month.
Yep. Looking forward to it.
See you next month. Nice to
And
see you
thank you,
all.
Raphael.